Hello, welcome to Numerical Ship and Offshore Hydrodynamics. Today is the lecture 52. Today we are going to discuss the ship hydroelasticity. Now, till today, previous class, everything we discussed about assuming the ship is basically a rigid body. Uh, this is okay with the small scale ship with 50 meter to 100 meter or 150 meter maybe, but nowadays there is a trend to go some kind of vessel which is having 400-meter long or something like this. In that case, we really cannot consider the ship as a rigid body. So, therefore, it is interesting to know that if we do not consider the ship as a rigid body, if we consider ship as a flexible body, then how the mathematics got changed and how we can do this fluid structure coupling. Okay. So, this is I am going to cover in today's some introductory class of course, and this is the keyword that you have to use to get this lecture. Before we start, let us start with a small demonstration. Do I write is an experiment? It is really not an experiment. So, to do this demonstration, I am using our departmental lab, which is the Ocean Engineering and Naval Architectural Lab. So, this is the tank dimension, is the length is 150 meter, breadth is 4 meter and depth is 2.5 meter. Now, let us see that what did I do. Now, actually I consider 3 different type of waves. Now, one is that when the wavelength is 3 times than the ship length. So, you can see that uh, it is we can consider as a low frequency region, right, because the lambda is 3 times larger than the ship length. Second one is we can say the higher frequency, because here the wavelength is the 3 times smaller than the ship length. Okay. So, let us see that in these two situations when actually the lambda is very big, the wavelength is much higher than the ship length, then what is happening. Okay. So, let us play this. Now, you can see here that wave is approaching, it is very low frequency waves. Now, you can see there is the shape does not response is very minimum, because this is the similar situation when actually you go into the sea and you take a bath, you simply just go up with the waves and you can come down with the waves. So, also you can see the phase is also 0. So, let us see that another situation when that high frequency phenomena. Here also you can see let us play it. Now, here you can also see that still that response of the vessel is not much, because its frequency very larger. So, it does not dissipate much energy, and you can see here that almost like a ripple. So, ship does not move much, right, it is not moving. So, now let us see when actually the ship length is equal to the wavelength. Now, in this situation let us see what is going to happen. So, it is not an experiment, because I did not measure anything, just to demonstrate you. Now, you can see here that now you can see now the response is very larger, and also you can see there is a phase between the waves as well as the ship. Now, here everything is very critical, like still it is not slam, or there is not much green water, there is not green water at all here, but at least it is the verge of that situation. So, you can see that how it is that rope also, now we have to have lot of stresses on the ropes, So, let us see once again, like just to check that how now here everything is under the rigid body. Now, if the ship is smaller, then I understand this one is okay, it is a rigid body mechanics is happening. Now, if the same thing is happen with the longer ship, then let us see what is going to happen. Now, it is a numerical simulation of our own code, this hydroelasticity code that we are discussing right now. Now, if you see here that now I am considering that is a flexible body. So, you can see it is not only having this phase lag and that abrupt motion, but at the same time it behaves like a flexible structure. So, because of this you can have some bending moment, or maybe sometimes I mean more serious thing is sometimes springing or whipping, many things can happen, and therefore, it is very important to understand the hydroelasticity of a body. That means that wave structure interaction considering the structure is flexible. So, since the introductory class, I would like to mention that it is so important in last couple of not couple of just last 1 or 2 decades, where people actually started building longer ship. Now, there is one you can say that very useful work by Hydroelasticity et al. They researched it and find out like there is a 43% of the people actually they are working on this hydroelasticity problem. So, one can understand that how important this for today. Now, it is the paper is on 2014. So, we have almost 10 years, but still it does not lose the importance. Okay. And there are some work that one should read before do anything in this particular domain, and I would like to some very useful work that one can see, like now some work here everywhere, some work actually is a analytical work. This one is very helpful for us because for the benchmarking. So, you can see that this work, if you look at it, that they are using some 2-dimensional body, the body is very regular as a circular disc or maybe a plate, and they apply the hydroelasticity on it. Okay. So, these are very good for benchmarking. However, if you want to do some kind of some practical work where try to figure out that hydroelasticity of ships. So, in that one has to go with some rigorous numerical coding. Now, these are some very pioneer work by Senjinovic or Futkara or the group by Getsuarez, and also the Koreans group the Kim. So, they have solved this problem using some kind of numerical technique. And here what we are going to discuss is that we have already developed a, I mean in last couple of previous lectures we have developed a not developed, we have discussed a numerical technique based on time domain panel method. Now, here what we are going to discuss is, suppose you have the rigid body code, how to advance it for the hydroelasticity, that actually the objective of this lectures. Now, once you have the rigid body, then you can actually think of incorporating this hydroelasticity or flexibility into the structure. For that, you need to have some knowledge of finite element also necessary. Here we really not into the finite element, however, which is necessary for to understand this particular methodology, that much definitely we are going to discuss here. So, the motivation actually here is that we have a rigid body code with us. So, now if you look at the all the literature, mostly either they are using some kind of frequency domain method. I mean, it is absolutely under the uh, linearity, and of course, even if the linear situation also very complicated. Okay. But here the advantage is this, we are going to do this in the time domain. Now, what is the difference between the frequency domain and time domain? At least at this point everybody know very well that in time domain that we can add some kind of nonlinear force in the equation of motion. However, if we use the frequency domain code, it is very complicated work to incorporate some kind of nonlinearity. For example, the last in this course we stop with incorporating the slamming and green water into the hydroelasticity solution. Now, this green water or slamming, those are not uh, periodic in nature, it is an impulsive load. Now, once this is impulsive load, so handling that thing in frequency domain is really difficult. So, therefore, that would be the more further motivation to understand the hydroelasticity in time domain. Okay. So, actually here in this course I actually frame two method, or you can see that the two approach actually. The first one is which is the direct coupled between the beam and FEM, that is what I am going to discuss initially, that I have my rigid body code. So, how I can use this rigid body code to address the hydroelasticity? This is the fundamental one. And once we develop the rigid body code, then you can see that it is not that complicated to incorporate the flexibility into the solution. Of course, there are many levels of complexities there, but at least you can capture the initial level, which is even fairly complicated. Now, in another level, what I am thinking of, like we can discuss, let us say I have a ship and I really do not want some rigorous analysis at the basic level, I mean at the initial level. So, I got the design. So, I need to estimate because I need to calculate the strength of the ship. So, what would be the thickness of the plate and many more things like. So, design load is very important for me, but at this point all this code is available here. For example, this sophisticated time domain codes or frequency domain codes or hydroelastic codes, these are not very cheap in terms of cost, availability, etc., etc. So, we really maybe in the initial level we really do not want to use such complicated or sophisticated software. Rather, let us the focus may be that I can get some kind of idea about what would be the range of the bending moment, what is the range of the shear force, like, and the stresses, etc., etc. So, if your motivation to get those things uh, in initial level, so we really do not need to use this complicated or sophisticated panel method code or this numerical code. So, for that actually we are going to discuss that we can actually, without making much compromise on the quality of the result. I mean, when you say the compromise means, like if you use the sophisticated method, definitely you can rely more on it. My point is, even if you do not use it, you use this semi analytic 3-dimensional time domain method, still you can get some very much realistic result, and the difference between this and that may not be that larger, so that you can think that okay, this is not gives a realistic value from. So, I should go for the complex sophisticated time domain solution, that you know it is not that bad as I said. So, both are maybe difference, but they agree. I will show you they are more or less within 10-15% or 20% at maximum. Okay. Now, let us start with the first one, and then after that we will discuss the semi analytic one. So, now how we can do this fluid structure interaction problem, this as follows. So, initially we have to make that the velocity, the displacement, the acceleration, that is our input. So, everything has to be initialized. So, we make it 0 everything, and then we solve the hydrodynamic problem. So, why I solve the hydrodynamic problem? Because by solving this I know the hydrodynamic pressure distribution over the hull, right. Now, this hydrodynamic pressure distribution is important because that is actually going to solve your structural problem. So, that would be the input. So, here you can see that here this solving this hydrodynamic problem and this get the hydrodynamic, not actually total force means total sectional force. Now, see, now it is I am not considering the rigid body, I am considering the body is flexible. So, I understand that here at each sections the velocity, the displacement, it is actually changing, right. Otherwise, normally if you consider rigid body, I am happy to know what is the force acting on here at the centroid, and then I multiply with the moment term r, and I can get the moment as well, right. And also if I know the here at this point what is the vertical displacement z, and if also if I know that the angular displacement theta. So, at any point I can find out my total displacement z p equal to z plus some L, the distance from here to the point I try to calculate what is, let us say this is the point, and if this length is L. So, it is L into theta, something like this, right. So, let me write in bigger way, so you just get it, something like this. This L is this distance between from the CG to that particular point. So, you can get the displacement of any point. This is fine when we consider the rigid body. However, for case of a hydroelasticity, that ship might bend in this way also, or maybe bent on this way also. So, in that case at each section it has different displacement, velocity and also, therefore, to get it I must have the hydrodynamic force on each section, the total hydrodynamic force. So, get hydrodynamic total force on each section, on each section. So, this is the input for me to solve the structural problem. So, then I start doing, either you can do the modal superposition technique, or we can use the advanced finite element method. So, we can get the so with this we can solve it, we can find out the structural displacement velocity, and this again we are going to use here for the solution of the problem, right. So, this is the overall flow chart of this of the hydroelasticity code, right. Now, here let us see that Today it is again like we just review of the previous thing. Now here you can see that boundary value problem is the same. You can see that all other, here we are taking the same thing, like we are using the total potential and then we are using the disturbed potential. Then 1.3 is nothing but your kinematic free surface bound, I mean the total free surface boundary condition, and then you have the condition infinity and you can have the condition at initial condition. So, this is fine. Where is the difference? Now, the difference here is actually when you write the body boundary condition. Now, when you are writing the body boundary condition in case of a rigid body, you can see that we are writing it is V into N. Now, this V is applied at the CG of the body. Here. So, V is not the function of x. So, what is happening here, in case of a flexible body, I have to apply this boundary condition at each x. So, this is the first changing from the rigid body problem. In case of a rigid body, we are having it is only a single point, which is C g, just one velocity of the rigid body which is applied as C g, and then we can use the boundary condition del phi del n equal to this. Now, here see del phi del n, now del phi del n is not the function, of course, the space, not the function of the time only, it is also the function of the space. So, this is a huge change, like, and one has to address this. So, this is the first thing that is different from the rigid body situation, right. However, otherwise if you understand this change, then remaining part more or less same, right. So, that we are using the same integral equation over here, you can see that 1.7 and 1.8, we are using the same integral equation for solving the phi, right. And also we are using the same equations to get the pressure as well as the force and moment, right. So, here in fact 1.110 also we need to change here, because this 1.10 gives you the force over the body. However, we are interested on the sectional force, right. We are not now, when you solve the hydroelasticity, we are really not interested on the total force, which is only for the rigid body. Now, this 1.10 also we need to change little bit. So, now we understand that it is almost the same code, the only thing that this body boundary condition we should be very careful where to put this 1.6, and then this 1.10 how to incorporate 1.10 to get the sectional force. Those things definitely we are going to discuss in details in later class. Okay. So, today we stop here and we continue with this time domain panel method for hydroelasticity in the next class. Okay. Thank you.